Okay, welcome back to our almost the end of our term in general chemistry, Chem 1331, spring term at the University of Houston. These are our COVID-19 quarantine, staycation, stay-at-home lectures. Like I said, I'm uploading these onto YouTube, and for those of you that haven't taken advantage of this, like and subscribe. The little thing off in the corner, right? And hit the little bell. Equals 1 extra credit point. Okay? That's supposed to be a bell. And this isn't just a cheap extra credit point. It's 1 extra test point of extra credit. Okay, that's a lot. That's an awful lot. So you can move your grade up just simply by paying attention and clicking like it. And there's only like 6 or 7 people that have taken the time and effort to watch these videos. And congratulations, you're doing the right thing. Those of you that aren't, well, I guess you're not getting the message anyway, so it doesn't really matter. I'm doing this because I want you to succeed and have the benefit of what I can give in terms of my instruction and insight into this material. So if you're not taking advantage of it, it's your tuition dollars down the drain. And anyway, let's move on. So today we're going to talk about the theory and structure of bonding in metals. We're all familiar with metals. We've seen them before. Here's a piece of copper. Okay. Here's a piece of steel. Okay. These are different materials. Copper doesn't have a magnetic moment. This has a magnetic moment. And so on. We can demonstrate the magnetic moment easily if I can find a compass. I usually have one on my desk someplace. But we're familiar with the properties of a metal. And the key with the metal, you notice it has a shine to it, a metallic luster to it, and it's malleable. I can bend it very easily. Here's another piece of metal. Maybe this is no. It's bendable. It conducts electricity, conducts heat very readily, and it's very firm and rigid, and can do a lot of things. A lot of properties with this. What we're going to talk about are what makes a metal in terms of its electronic properties, where the electrons are. So the key approximation that we make is that for the most part, the nuclei, the atom sites in a metal are fixed. This isn't flowing. It's locked into some sort of roughly crystalline structure. There's some grain boundaries. If you were to look, pull this up, clean the crud off of it, and look at it at a microscopic level, you would see grain boundaries that we understand. But within that grain boundary, you would see packing in a crystal structure, and all the iron and steel and the iron mostly atoms inside this and the copper atoms in this are located in their periodic arrangement. The electrons, however, remember we have bonding and non-bonding electrons. These are the valence electrons. Are very mobile. So the outermost electrons in the surrounding the atoms of the iron atoms in this bottle opener, for the most part, are freely movable, are free to move about. They have a kinetic energy. They exist much like a gas, and what's sometimes called the electron sea or the electron gas model for metals. and it's still it's charge neutral. There's a, so what we can imagine is that this piece of iron is really a periodic arrangement of iron atoms with the countercharge of iron ions with a comparable number of electrons that are free to move around in the system. And what I'm going to do is talk about what's called the band structure of this, and because it's related mostly to how we think about things in chemistry, but it's also a powerful way to understand the electronic structure of metals. And I'm going to use some mathematics and use some quantum mechanics to do that. And the idea is this. So imagine that I have each atom site, which I'll represent as a circle, and it continues on in one dimension, and this is going to be the distance x along that coordinate, and these are spaced some distance a away from each other. Okay. Now at each local site, I would imagine that I have an orbital, which we'll say this is site n, this is site n plus 1, this is site n minus 1. And at each site I have an orbital phi n, this would be phi n plus 1, phi n minus 1. So these would be like some molecular orbital or some atomic orbital that I have located on each of these atom sites. They're spaced exactly distance a away from each other, and I can label them by which atom they happen to be associated with. Okay? Now, if we neglect we're going to neglect electron-electron interactions, and that's a pretty good approximation. The reason for that is that because each of these sites are really like a plus 1, I'm going to have one electron from each site associated with each. So let me restate that. So imagine that this is a plus charge. Each one of these is a plus 1 ion, and contributes one electron to the electron C, the electron gas that's going to be mobile around this. So that the whole thing is charge neutral. So if I have n, capital N, number of ions in my system, I have to have the same number of electrons to make sure that the charge balance is neutral. Okay, so we're going to assume each site has one electron, as each site is a plus 1, contributes one electron. We're going to neglect electron interactions, and the reason we can do that is because the electrons are mostly screened from each other by the background of all the positive charges. They interact with the positive charges and the negative charges, and they see a very weak background of interaction. There's a little bit. It's important. It's very important in higher densities, but for the most part, we can neglect it and to a good approximation. And what we do then is we can write out a Schrodinger equation for that by assuming in the following way. I'm going to assume that an electron sitting on site n has an energy. So an electron at atom has energy En. Okay, that's the energy to put an electron into one of those orbitals. Let me scoot this up. Okay, that's the energy to put an electron into that orbital. And then I'm going to say that an electron can move neighboring orbitals Okay? And there's an energy associated with that. And that energy is going to be T. And T. T. This is the energy associated to move, and it's going to be some number less than 0. So in other words, it's energetically favorable to delocalize. Okay, and this again one of the assumptions that we made when we were developing the molecular orbital theory for atoms, right? That we can put an energy and so on. But what we're going to do is a little bit different in this case. Is that so let me write out the resulting Schrodinger equation. We get this is that the En times phi n plus T phi n minus 1 plus phi n plus 1 is equal to the energy times phi n. Okay, that's the Schrodinger equation. For this, okay? And we need to solve for En and phi n's and everything else. So the key, though, is that for a periodic system, all these energies, En, all these energies are the same. All the atoms are identical, and the other thing which I can say is that phi n is related to phi n minus 1 and phi n plus 1 in the following way: is equal to e to the I k times the lattice spacing of phi n minus 1, and it's equal to e to the minus I k a phi n plus 1. So this is what's called translational invariance. So I can relate the function at one site to the function at the other site. Okay, and A is the lattice spacing. A is the lattice spacing. Okay. Now I can take this and plug it in, and what do I get? Well, I get a En phi n plus T. Well, phi n minus 1 is e to the I k a phi n plus e to the minus I k a phi n is equal to capital E, the total energy, the energy of the system, the energy of the electron, phi n. Now you notice that this cancels, that cancels, that cancels, and that cancels. In fact, let's write this En as simply the energy to put it into any of the sites. So therefore, the energy as a function of k, which is the momentum, the wave number of the electron, is equal to E, the site energy, plus T times 2 cosine theta, or cosine K A. Okay? Now, that's it. Now, what that means is that if I know the wave number of my electron, I can plot this. So this is pi over 2. This is the number k times a, and minus pi over 2. Okay, so t is a negative number, so 2t is down here, and I get a cosine curve. I get a cosine curve this way. Okay, so this is at E0, and this is at minus 2t, or at 2t. This is at plus to absolute value of t. So I get a band. That's between, let me write this down here, minus 2 times the absolute value of t. So is that energy right there. This is at the top of this band is at plus 2 times the absolute value of this energy to move an electron, the delocalization energy of the electron. Now, each site contributes 1 electron. Okay, that means that that electron can be moving this way in plus Ka, or it can be moving in minus Ka. I don't know, but I can fill up for every electron. I can start filling these up. And remember the Pauli exclusion rule, right? Well, that electron can have one of 2 spins. It can either be spin up or it can be spin down. So consequently, I start filling up all of these energy levels. These are all continuously packed energy levels all the way up until I get to the half-filled part. So these are all the plus minus spin quantum states that can be filled up by the electrons. So if I were to discretize this, I would have n, total of n number of states. I would have filling of n over 2 because of spin, and that puts me right here in the middle. Now you notice something about the energy. At that point right there, there's no energy difference. These are empty. These are filled. Okay, there's no energy difference between an empty orbital, the empty orbital at k times a equals pi over 2 plus a little bit, and the filled orbital exactly at pi over 2. K times a equals pi over 2. So there's no energy gap. No energy. It takes almost no energy whatsoever, a minuscule amount of energy to promote an electron that's down here in a filled orbital to an empty orbital. So the energy gap in a metal is functionally 0. It's effectively 0. So it takes almost, so even at thermal energies are sufficient to populate and deplete the filled orbitals and put electrons into the empty orbital. So in terms of the parlance of metals, these are called conduction, and these are the valence band. These electrons in the conduction band are free to move around, and it's a continuum. It's not a virtual continuum. It is a continuum of states between that are packed into all of this. Okay, so in the illustration to the left, we can see how this builds up. If I were to have 2 atoms in my system, I would have 2 energy levels. If I had 4, I have 4. If I have 16, if I have all of these guys, but all of these 10 to the 23rd energy levels are packed in this little band. So they're all scrunched in there from minus this energy up to up to that energy there. They're not over. It's not a continuum like you would have in free space. They're constrained because of this periodicity, this interaction that's required by the fact that I have a periodic array of ions. Okay. Now we can make this more quantitative. We can put in the actual functions if we would, and that's sketched over here in figure 9.20, where we have each one of the sites that I had drawn in over here is now actually represented by a deep potential well that can maybe have some localized states, which are, let me just maybe I can sketch this off to the side. So on this picture here, I have a magnesium atom which has plus 12. Okay, and it has a very deep Coulomb well going down like that. Okay, and this is the Coulomb potential. Okay, and just like, you know, it has energy levels that are localized. So the energy levels inside the well, these are localized atomic states. But if I have another guy over here, it also has a Coulomb potential, and it has equivalent levels of localized atomic states over there. And as I get closer to the top of these wells, I get this, the electrons that are over here can hop over to here, can hop over to here, and then so on and above this. I might have more states that are up here. And these would be and these states all the way up to the top of that potential are occupied molecular orbitals, and these are unoccupied. You can't see what I'm drawing. Okay, these are, and so if I wanted to calculate this T, this is my T, and of course this continues all the way up to because it's a metal, and then the difference between the bottom of that and the top of that is well, this is minus 2T and that's plus 2T. And then the energy to put an electron there is whatever energy that happens to be. So mathematically and physically, this all makes sense. This provides a one-dimensional, you can extend this into 3 dimensions, you can be more sophisticated and make a more complicated lattice structure, but this is how we describe the electronic states. This is the simplest description of electronic states in a metal. And it works very well. Now the reason is to continue on with what makes a metal is that in a metal, let me go back to my picture that I have back here. If I look at the energies that I sketched of the metals, maybe I can draw another picture of this. The energies and I can also go in the negative direction over here, minus pi over 2. Okay. Okay. There's no energy difference between these filled versus empty orbitals. And if I look at the distribution, the occupancy of an orbital versus its energy, I would get to a point right there. Okay, so here's the energy. Here's the energy, and this is starting off at minus 2T. This is going to be at E0, and all the way up to plus 2T. I would get something that would start off an occupancy of 2. Well, of 2, right? Because I can put 2 electrons per orbital down here at some energy. And this continues on until I get right to there, and boom, it stops. So all of these are filled. 0. How many electrons do I have in? So this includes, spin up and spin down electrons in and each one of these energies, I have two. And so I get to that point, boom, I stop. Now at finite temperature, what can happen is that this can roll off a little bit, and this can fill in. This is at finite temperature. And this energy, by the way, just to is called the Fermi energy. Okay, that's the Fermi energy, and that's named after Enrico Fermi, one of the sort of founders, if you would, of modern atomic theory, modern quantum mechanics, and modern physics. But at finite temperature, these I get a depletion of these, and I start occupying, and this is one of the reasons why I get high conductivity of metals, is because I have freely, even at finite temperature, I have freely moving electrons in these unoccupied orbitals that are free to move around the system, and almost unhindered through the system. And that's how I start getting the metallic behavior. Now, if I were to introduce impurities into this system, I can start mixing different elements and create different kinds of materials by knocking one electron, maybe knocking one atom out of its site, or maybe I can pack in other elements into different sites. And there are two different kinds of ways I can do this. These are called alloys, by the way. And by the way, most of the materials that we have are alloys. This is some sort of an alloy. Copper is a metal, but it's alloyed with probably nickel or something that's not pure copper, with something else. And this gives rise to all sorts of different kinds of material properties of metals. Now, there are two types of alloys called substitutional alloys, where you simply knock out one of the lattice-sites and replace it with something else. Or what's called an interstitial alloy, where I have the lattice structure of copper or whatever I'm going to have, but I pack in an extra atom and its electrons someplace into one of the holes of a close packed metal structure. And steel is an example of this. So carbon steel is where I packed in carbon into the interstitials between irons, and the amount of carbon in a system determines the properties of the carbon steel. It makes it more brittle, less brittle, more malleable, less malleable, and it's what gives rise to the properties of knives and steel objects. Okay, so for example, brass is an example of an interstitial or of a substitutional alloy, where I replace copper and zinc to make brass and bronze and other kind of things. And zinc or steel is where I've taken the iron hexagonal closest packed, and every once in a while I sprinkle in a carbon someplace in a little vacancy site. It's not a vacancy site, it's a little interstitial site, one of these little holes, because carbon's a small little atom, and copper and zinc are about the same size, so they can you put a zinc in, it knocks the copper out, and but a carbon can fit nicely inside of this, and the density of carbon that you have determines the properties of the steel. And like I said here, so mild steel is nails and cables and chains, it's something I can move, and I have high carbon steel, which is a knife. But you change the brittleness of a steel. So a really good knife or a sword or something like this is a combination of different kinds of materials. It's hard steels and soft steels and high carbon steels where you need it. You can also have network solids. And a network solid is like diamond and graphite. I want to move ahead and continue to talk about the electronic structure, and I'll come back to the network solid part in a different discussion. So let me move forward. Okay, so here we go. Now diamond, you look at diamond and you realize, oh hey, this is a nice periodic structure. Why isn't diamond like this? Why isn't diamond also a metal? It's clear. It's very brittle. Um, you can break it apart, but it's a hard substance. Um, but I mean, it's one of the hardest substances. You can break it into crystalline pieces. And it's a network solid. It's a network. It's like all of the atoms form one gigantic molecule, if you want. But the electrons are localized in this particular case. It's not a metal. Even though it's periodic, it's not a metal. And the reason for that is in a metal, you see how this energy difference between the filled molecular orbitals and the empty molecular orbitals. And what differentiates a metal from a non-metal is the fact that there's a gap. Okay? This energy gap. If there's a gap, it's not a metal. Okay? Now, whether the kind of metal it is. Now, most metals actually have a gap, a little bit of a gap. If that gap is small compared to thermal energy, then that gap is still considered a metal. If that gap is large compared to thermal energy, then you have either an insulator or a semiconductor. So that's what I wanted to talk about in terms of the insulators and semiconductors. Diamond is an insulator. It takes an awful lot of energy to put an electron into this, to promote an electron from a filled molecular orbital into this empty molecular orbital. It's clear. You know, the only reason you get colors in a diamond is if you have an impurity, and it's so if it's since it's pure, or since it's clear, the energy gap roughly between the molecular orbitals and the filled molecular orbitals and the empty molecular orbitals is large compared to visible light energy. And visible light energy is between 1 to 3 electron volts, let's say. Thermal energy is much less than that. Thermal energy is like a couple of millivolts. So the optical gap, or the gap between the filled molecular orbitals and the empty molecular orbitals in a substance like diamond is tens of thousands times greater than the thermal energy. So it's an insulator. But not all forms of carbon are diamond. You can also have graphite. And we can also represent this as a three-dimensional model, where instead of having sp3 hybridized orbitals, we have sp2 hybridized orbitals in a plane and one perpendicular. We can see this. Here we go. This is the structure of graphite. And in graphite, you see, I have this almost like metallic type case. It is a so my pencil is graphite. You can see this sort of gray. Maybe you can see the shine. And so what pencil lead is what pencil lead is basically graphite that's been mixed with clay or some sort of binding agent. And the reason graphite works so well as a lubricant, it slides right off, is that these planes of sp2 bounded carbon are basically free to slide back and forth over the top of each other, just like my hands are free to slide back and forth over the top of each other. But there's a very strong bonding within the layer, and within the layer I have this delocalized network of what's called a pi bonding network, and the description of that is very much, in fact, it's exactly the way we described this model up here. It's just a little bit more complicated because it's hexagonal, but you wind up getting an almost metallic like behavior in the plane, in the p orbital plane, and an insulating behavior moving perpendicular to that. So within this hexagonal plane, these pi stacked planes, electrons are more or less metallic. It behaves very much like a metal, and between the planes, it's more insulating. And this is one of the surprising properties of graphite, and gives rise to some really interesting properties of graphite. And in fact, graphene, which is a single layer of graphite, is one of the more widely studied materials today, because it has some very interesting electronic properties that people are studying very, very actively today for light emission and light harvesting applications, and all sorts of different kind of optical electronic properties. It's a very fascinating material. Silicon is another kind of material that we look at now, and it's useful to look at. Now, it's similar to to diamond, but it also forms what's called silica. Silica is SiO2, which is basically glass. Okay, glass is mostly a network of SiO2 tetrahedra. In the following, quartz glass, for example, is SiO2, and it's simply chains of SiO4 tetrahedra that form a network. And again, it's an insulating material, much like graphite, or much like diamond. But silicon is let's go forward to this, is an interesting material, because you see, when you add in electrons or add in atoms to the vacancies, you still need to be charge neutral, and you might add extra electrons, and you might add electrons that are between the filled and empty bands, okay? Or you might deplete those the filled molecular orbitals, again, to make things charge neutral. For example, if I put ions into the system, I might deplete. I might pull some electrons out of the filled orbitals, and I would have what are called holes, electron vacancies. And it's these excess electrons and holes that give rise to N-type or P-type semiconductors. N-type simply means I've added negative charge, and P-type means what moves are actually positive charges. So the N-type means that the negative charges are moving, and P-type means that the positive charges are moving. So these electrons that are in this band are easily promoted into the conduction band, and likewise these electrons, really what you wind up getting are doping levels down here that aren't shown in terms of occupancies, but that deplete these electrons, and it's these depleted electrons that become mobile. The positive charges, the holes, are mobile. Positive mobile, negative mobile. So if you stick an N-type material with a P-type material, for example, if I dope silicon with something that's N-type and I dope silicon with something that's P-type, I slap them together, I form what's called a PN junction, or I can make more elaborate junctions by having a bias across the system, or having something that can gate the qualities, or the type of semiconductor that I have, by injecting or removing electrons from the system. I can form what's called a diode, and so I can have current can flow in one direction more easily than the other, and that is called a diode. So every electronic component, semiconductor electronic component that we have, is essentially a hybrid material between P-type and N-type materials, usually silicon, sometimes gallium arsenide, and other sort of more mostly silicon, but some a little bit more exotic materials. Silicon being the easiest to work with. and it's the mobility of the p-type and n-type holes, or p-type charges or holes, and n-type electrons that give rise to the semiconducting properties of a material. Under forward bias, I get one kind of charge flow, and under reverse bias, it might be easier or more difficult to move charges. And so, by looking at the current voltage characteristics, I can understand the properties of a diode. And if you want, you can look up what's called the Shockley-Quisar equation, or the diode equation, and this gives you a understanding of how silicon-based solar cells work. I'm going to end here. Next time I'm going to pick up and talk about molecular solids, and next week we'll talk about more thermodynamics of gases, and with that we'll almost be ready to end the term. So stay safe, keep up, and remember, click subscribe, click like, and get some extra credit points. Okay? Good luck.